there is no empty direction in the sky. Wherever an observatory turns, light arrives from somewhere. It comes from nearby stars, from clouds of gas between the stars, from distant galaxies, and from matter heated long before the Earth existed. Even the spaces that look black to the eye are crossed by radiation, particles, and the faint afterglow of the early universe. Yet, among all that natural activity, one kind of evidence has not appeared. No signal has been confirmed as a message from another civilization. No telescope has found an engineered structure whose origin can be separated from nature. No probe, artifact, or industrial trace has been verified beyond Earth. There have been interesting candidates, brief signals, unusual stars, and observations that deserved careful attention. None has survived the long process required to become proof of extraterrestrial technology. That absence is often called the Great Silence. The name can be misleading because the Milky Way is not silent at all. Stars flare. Pulsars send regular beams across space. Gas clouds glow at radio wavelengths. Exploding stars release energy that travels for thousands of years. The silence refers only to the lack of a confirmed technological voice within that immense natural conversation. This would be less puzzling if planets were rare. They do not appear to be. Astronomers have now confirmed more than 6,000 worlds beyond the solar system. Even though our searchers have examined only a small part of the galaxy and favor planets that happen to reveal themselves through detectable orbits, the larger pattern suggests that planets are common companions to stars. The Milky Way contains more than 100 billion stars, and current evidence indicates that planets may outnumber them. Those numbers do not tell us how many living worlds exist. A planet can be rocky and still have no ocean. It can orbit within a habitable zone and carry an atmosphere that is too thin, too dense, or chemically hostile. Life may begin readily, or the first living chemistry may require a sequence so improbable that it has happened only once in our part of the cosmos, and life is only the beginning of the chain. Microbes are not forests. Complex organisms are not necessarily intelligent. Intelligence does not guarantee technology. Technology does not guarantee radio, interstellar travel, or any activity visible from another star. A civilization may endure for millions of years, or remain detectable for only a few generations. It may expand, stay home, communicate narrowly, or produce signs we have not learned to recognize. The Fermi paradox grows from the tension between possibility and observation. The galaxy is old, large, and rich in planets. Some planetary systems formed long before the Sun. If technological societies arise often, last for long periods, and leave evidence that spreads through space, then at least one of those traces might be expected to have reached us by now. But expectation is not detection. The missing evidence could mean that life is scarce. It could mean that intelligence is rare, that civilizations are brief, that interstellar expansion is uncommon, or that our instruments have searched too little of too much sky. It could also mean that the assumptions inside the question were shaped too closely around human behavior. Tonight we will not treat the darkness as an answer. We will treat it as a boundary around what is known. Beyond that boundary lie equations, telescopes, evolutionary bottlenecks, possible technologies, and several ideas that range from scientifically grounded to openly speculative. Each offers a different way to understand why a galaxy filled with worlds has not yet answered. For now, the only honest starting point is simple. We have learned that planets are abundant. We have not yet learned whether anyone is there. The puzzle becomes clearer when the Milky Way is viewed not only as a place, but as a clock. Our galaxy is roughly 100,000 light-years across. A beam of light leaving one side would need about 100,000 years to reach the other. That interval is far longer than recorded human history, yet it is brief beside the age of the galaxy itself. The oldest stars in the Milky Way formed more than 13 billion years ago. The Sun appeared much later, about 4.5 billion years ago, after earlier generations of stars had already lived, changed, and returned newly made elements to space. Those older stars helped create the ingredients from which rocky planets could form. Carbon, oxygen, silicon, iron, and other heavy elements were produced within stars and scattered through the galaxy. New systems gathered that enriched material into planets, moons, atmospheres, oceans, and countless arrangements that no telescope has yet seen closely. Some planetary systems may therefore have had billions of years more than Earth. That additional time does not guarantee life, does not guarantee intelligence, engineering, or a desire to cross interstellar space. But it creates an uncomfortable possibility. If even one civilization arose long before humanity and began moving gradually between stars, the Milky Way may have offered enough time for its influence to spread widely. The journeys would not need to resemble the swift voyages of fiction. A spacecraft traveling at 1% of the speed of light would still exceed anything humanity can currently build. Even at that speed, a trip to a nearby star might take several centuries. The passengers, if there were passengers, could not expect to return home. Machines would need to endure long periods without repair. Dust grains striking at high speed could become serious hazards. Radiation would slowly damage electronics, structures, and living tissue. Yet the distance between neighboring stars is not usually the width of the entire galaxy. It is more often a few light years. A civilization would not need to cross the Milky Way in one uninterrupted flight. It could travel to a nearby system, establish a settlement or automated base, gather local material, and eventually send another expedition onward. Each new destination could become another point of departure. The pattern would grow as a branching network. At first, there might be only one home system and one distant outpost. Later, there could be several. Each would move independently, making its own decisions and preparing its own machines. The process could pause for centuries or millennia between launches and still continue across a small fraction of galactic history. Even tens of millions of years would leave most of the Milky Way's lifetime untouched. This does not show that such expansion has happened. It only reveals why the galaxy's age matters. A process that appears impossibly slow within one human life may look almost brief when placed beside billions of years. Stars also move. The Milky Way is not a fixed field of lights, resting in permanent positions. Every star follows an orbit through the galaxy. Over long intervals, systems that are now widely separated may pass closer together. Other neighbors slowly move apart. The routes available to a traveling civilization would change as the galaxy turned. A society might wait for favorable passages rather than attempting the most difficult crossings. A probe could travel when two stars approached within a manageable distance. A settlement that once seemed isolated could later find new neighbors moving through its region. Computer models of galactic settlement often produce patterns more complicated than a wave sweeping evenly across a map. Some areas become well connected, others remain unvisited. Expansion can stop, restart, fragment, or fade. Civilizations may disappear while their machines continue. Settlements may lose contact with their origins and become independent long before they reach the next star. The result need not be a single empire. It could be a scattered history of probes, small communities, abandoned installations, and brief periods of movement, separated by long intervals in which almost nothing happens. Earth might lie within one of the missed regions, or our system might have been examined so long ago that any evidence has vanished, become buried, or remained somewhere we have never looked. These possibilities are difficult to test, and they can become too convenient when used without evidence. A claim that something is hidden cannot be confirmed simply because it has not been found. Still, the settlement argument exposes the reasoning at the center of the paradox. The galaxy is old enough that speed alone may not explain the absence. In the summer of 1950, this tension appeared during a lunch conversation at Los Alamos in New Mexico. The physicist Enrico Fermi was eating with several colleagues. Their discussion had wandered through reports of flying saucers, a newspaper cartoon, and possibility of travel between stars. They considered distances, spacecraft, and the amount of time available to an older technological society. At some point, Fermi asked a short question: where is everybody? The precise wording is uncertain. Memories of the lunch were recorded years later, and the participants did not recall every detail in the same way. Fermi did not publish a formal theory under the name now attached to him. His question was more immediate than that. If interstellar travel was possible, and if other civilizations had appeared before us, why was there no obvious sign that any had arrived? Fermi was known for approaching large questions through rough but useful estimates. Instead of requiring every detail, he would divide a problem into smaller parts and ask what order of magnitude made sense. The Milky Way was old. Neighboring stars were separated by distances that advanced machines might cross. New settlements could become new launching points. Given enough time, even a slow expansion might reach a large portion of the galaxy. The absence of visitors then became something that required explanation. Later writers widened the question. They asked not only why no spacecraft had appeared, but why no other technological trace had been confirmed. A civilization might never visit Earth and still release radio signals, build powerful energy systems, alter planetary atmospheres, send automated probes, or create structures visible across interstellar distances. The modern Fermi paradox includes all of these possibilities. It does not state that extraterrestrial civilizations must exist. It does not prove that expansion is inevitable. Its force depends on assumptions about how often life begins, how intelligence develops, how long technology survives, and what advanced societies choose to do. Remove any one of those assumptions, and the puzzle changes. Perhaps no one begins the journey. Perhaps many begin, and very few continue. Perhaps the galaxy contains travelers, but settlement is uneven enough to leave entire regions untouched. Perhaps civilizations become difficult to notice before they ever reach another star. The old age of the Milky Way does not settle the question. It only gives every possible answer a very long time in which to unfold. The question of who might be out there becomes easier to hold when it is divided into smaller questions. That was the purpose of the Drake equation. It did not begin as a prediction. It began as a way to organize a meeting. In 1960, astronomer Frank Drake was working at the National Radio Astronomy Observatory in Green Bank, West Virginia. There he carried out one of the first modern searches for radio signals from nearby stars. The experiment was called Project Ozma. Drake aimed an 85-foot radio telescope toward two stars, Tau Ceti and Epsilon Eridani. Both were relatively close to the Sun, and both seemed like reasonable places to begin. At the time, astronomers did not know whether either star possessed planets. They did not yet know whether planets were common anywhere beyond the solar system. The telescope listened near a frequency associated with neutral hydrogen. Hydrogen is the most abundant element in the universe, and Drake reasoned that another technological species might also recognize its radio signature as a natural meeting place. No confirmed message was detected, but the search demonstrated that the question could be approached with instruments, rather than imagination alone. The following year, a small group of scientists gathered at Green Bank to discuss the search for extraterrestrial intelligence. The participants came from astronomy, physics, chemistry, biology, and engineering. Each discipline held a different part of the problem. Astronomy could estimate how stars form. Planetary science could consider possible worlds. Biology could ask how life begins and changes. Technology and history could help frame how long a civilization might remain visible. To guide the discussion, Drake wrote down a sequence of factors. The result later became the Drake equation. In spoken form, it begins with the rate at which suitable stars form in the Milky Way. That number is then multiplied by the fraction of stars that possess planets. The result is multiplied again by the average number of worlds in each system that might offer conditions where life could exist. After that, the equation enters territory that is much harder to measure. It asks what fraction of potentially suitable worlds actually develop life. Then, it asks what fraction of living worlds produce intelligence. Then, what fraction of intelligent species create technology that can be detected from a distance. Finally, it asks how long that detectable period lasts. The last factor may be the most powerful of all. A civilization that releases noticeable signals for only 100 years presents the galaxy with a very narrow window. Another society would need to be listening in the right direction, at the right frequency, during that brief interval. A civilization that remains detectable for 1 million years creates a far larger target in time. Its radio beacons, lasers, atmospheric changes, spacecraft, or energy use might remain available to distant observers across many geological ages. Even if such civilizations were rare, long lifetimes would increase the chance that two of them existed at the same time. A short lifetime can make a frequently inhabited galaxy appear empty in the present. The structure of the equation matters because the factors are multiplied rather than added. Imagine a large number of planets that begin as possible homes for life. If only a fraction develop biology, the group becomes smaller. If only a fraction of those living worlds produce complex organisms, it shrinks again. Intelligence narrows it further. Detectable technology narrows it once more. None of the individual steps has to be almost impossible. Several moderately uncommon steps multiplied together can produce a very small final number. The reverse is also true. If planets are abundant, life begins easily, intelligence appears often, and technological societies remain visible for immense periods. Then the equation can describe a Milky Way containing many civilizations at once. The equation does not decide between these possibilities. It reveals where the uncertainty lives. The first astronomical terms are now understood more clearly than they were in Drake's time. Planet searches have shown that worlds form around many kinds of stars. Some systems contain small rocky planets. Others hold gas giants, tightly packed orbits, or arrangements unlike anything around the Sun. This progress has removed one old uncertainty. Planets are not unusual accidents, but knowing that planets exist is very different from knowing how many can support life. A world may orbit at a distance where liquid water could remain on its surface and still be dry, airless, or chemically hostile. Its atmosphere may trap too much heat or too little. Its star may produce intense radiation. Its climate may shift beyond the limits that complex chemistry can tolerate. Moons may also matter. Some could contain oceans beneath ice, warmed by the gravitational pull of nearby planets rather than by direct sunlight. These environments widen the range of places where biology might be possible, while also making detection more difficult. Beyond habitability lies the origin of life. Here, the equation reaches one of its deepest unknowns. Life appeared early in Earth's history, once the planet had cooled and stable environments had developed. That timing could mean that biology begins readily when conditions allow it. It could also mean that Earth experienced a rare event very early, and that observers can only arise on worlds where such an event happened soon enough to leave time for evolution. With only one known living planet, the two interpretations cannot be separated. The next step is no easier. For most of Earth's history, life remained microscopic. Complex organisms arrived much later. Technological intelligence appeared later still, after billions of years of biological change. Evolution does not appear to move toward radio telescopes as a planned destination. Many species survive successfully without developing language, metallurgy, mathematics, or astronomy. Intelligence may be useful in some environments and unnecessary in others. Even a highly capable species may lack hands, fire, accessible materials, or the social structures needed to preserve knowledge across generations. And technology does not guarantee visibility. A civilization might use communication systems that release very little energy into space. It might rely on narrow beams rather than broad broadcasts. It could live beneath an ocean, inside artificial habitats, or in regions where its activity blends into natural background radiation. Detectability is therefore not only a question of intelligence, it is also a question of engineering, behavior, duration, and chance. The Drake equation remains valuable because it refuses to hide these uncertainties inside a single guess. It places them in sequence where each can be examined on its own. It turns one large mystery into several smaller ones. How often do suitable worlds form? How often does chemistry become biology? How often does biology become intelligence? How often does intelligence become visible? And once a civilization can be noticed, how long does it remain that way? The equation offers no final number. It offers a map of everything we still do not know. There is another way to approach the silence. Instead of asking what an alien civilization might be like, astronomy can ask what technology does to its surroundings. Technology moves energy. It changes matter. It produces patterns that natural processes do not usually make. Some of those patterns may remain visible across interstellar distances, even when the people or machines responsible for them never intend to send a message. Scientists call such evidence a technosignature. A technosignature is not proof by itself. It is an observation that could point toward technology after natural explanations, human interference, and instrumental errors have been carefully tested. The distinction matters because the universe is inventive. Stars pulse. Magnetized planets produce radio emission. Dust absorbs light and releases it again as heat. Chemistry can create gases that appear unusual before their origin is understood. The search therefore begins with possibilities, not conclusions. Radio remains one of the clearest possibilities. Many natural objects emit radio waves, but their signals often spread across broad ranges of frequency or change in ways connected to known physical processes. Technology can create much narrower transmissions. A signal concentrated into a thin band can stand out from the wider radio background, especially if it repeats or carries a structured pattern. A distant civilization might build a beacon designed to be noticed. It could transmit toward nearby stars, perhaps returning to the same targets at regular intervals. It might choose a frequency with physical meaning, such as one associated with hydrogen, hoping that another scientific society would recognize the choice. But a signal need not be a greeting. Radar used to study planets or track objects could escape from a planetary system. Communication between distant settlements might briefly cross Earth's line of sight. A powerful transmitter could be aimed at a spacecraft, a moon, or another planet rather than at us. We might notice only because the beam continued beyond its intended destination. This kind of accidental detection depends on geometry. A narrow beam can travel far while remaining strong, but it illuminates only a small part of the sky. Earth would have to be in the right direction at the right moment. A broad transmission reaches more directions, yet its energy becomes spread across an expanding sphere and soon becomes difficult to separate from noise. Humanity's own radio presence shows the difference. some of our strongest planetary radar transmissions could be noticed from farther away than ordinary television or mobile communication. Much of modern communication is carried through cables, satellites, compressed signals, and directional links. A civilization can become more connected on its own world while becoming less obvious between the stars. Listening is therefore a problem of both sensitivity and patience. A radio telescope may examine one star for a few minutes while a distant transmitter is silent. It may listen at the wrong frequency or search for a signal that drifts slightly because the transmitting planet is rotating and orbiting its star. It may record something promising that later turns out to come from a satellite, an aircraft, or equipment on Earth. The search space is immense. There are billions of stars, countless possible frequencies, many kinds of signal, and long stretches of time. To say that no radio message has been confirmed is not to say that the whole galaxy has been listened to. It means that a small and carefully chosen portion has been examined with instruments whose abilities continue to improve. Visible light offers another path. A sufficiently powerful laser can produce a pulse that briefly outshines its host star within a narrow range of wavelength. The pulse might last only a fraction of a second. If it were directed toward Earth, a telescope designed to notice rapid flashes could separate it from the steadier light of the star. Lasers might serve as beacons, but they could also be tools. A civilization could use them to communicate between planets, transmit energy, measure distant objects, or push lightweight spacecraft. None of those activities would need to include humanity. The beam would only need to cross our view. Optical searches face the same difficulty as radio searches. A narrow signal is efficient, but easy to miss. The receiving telescope must be looking at the correct place during the brief interval when the light arrives. Technology may also leave slower traces. An industrial civilization can alter the atmosphere of its planet. Certain artificial chemicals, if produced in large amounts and maintained over time, might absorb specific wavelengths as starlight passes through the air. Future telescopes could search for combinations that are difficult to explain through ordinary geology, biology, or stellar activity. Even then, caution would be required. A gas that appears artificial on Earth may have an unknown natural source elsewhere. Different planets have different interiors, oceans, surfaces, and chemical histories. One unusual molecule would rarely be enough. Researchers would need to examine the entire atmosphere and the environment around it. The strongest case would come from several clues agreeing. A planet might show a chemically unusual atmosphere, a recurring narrowband signal, artificial-looking illumination on its night side, and an orbit filled with objects whose arrangement could not be produced naturally. Each clue would still need testing, but together they would become harder to dismiss. Artificial light is a demanding target. Cities on Earth are bright to nearby satellites, yet from another star they would be hidden beside the sun's reflected light. A distant observer would need sensitive instruments and favorable geometry to separate the night side of Earth from the much brighter day side. A civilization illuminating a large fraction of its planet, or using light unlike the glow of fires, lightning, or auroras, might be easier to notice. But the scale would have to be enormous, and the observation would remain difficult. Larger engineering could be more visible. In 1960, physicist Freeman Dyson suggested that an advanced society might capture a significant portion of the energy produced by its star. The popular image is a rigid shell enclosing the star, but such a shell would create severe structural problems. A more plausible form would be a vast swarm of independent collectors, habitats, or machines following separate orbits. The important idea is not the shape, it is the energy. If structures absorb starlight, and use it for work, computation, industry, or habitation, the energy must eventually leave again in another form. Much of it would emerge as heat at infrared wavelengths. From far away, the system might appear dimmer in visible light and unusually bright in infrared. Astronomers can search for that imbalance. But dust around stars also absorbs visible light and releases infrared radiation. Young stars, dying stars, planetary debris, and thick clouds can all create natural heat signatures. A candidate would require detailed study of temperature, spectrum, age, location, and surrounding material. No confirmed Dyson swarm has been found. That absence tells us little about smaller civilizations. A society using only a tiny fraction of its star's energy could remain far below current detection limits. The search is most sensitive to large and conspicuous engineering, not to efficient communities living within a modest planetary system. This limitation appears again in the Kardashev scale. The scale classifies hypothetical civilizations by the amount of energy they use. One level approaches the energy available across a planet. Another approaches the output of a star. A third extends across a galaxy. The scale is useful because energy use can affect visibility. A civilization drawing power on a galactic scale would be more difficult to hide than one operating a few settlements around a single moon. Yet there is no law requiring technological development to climb endlessly upward through greater consumption. Progress could take another direction. Machines may become more efficient, populations may stabilize, computation may increase, while physical construction becomes smaller. A long-lived civilization might use less visible energy than a younger industrial society. It could direct waste heat away from observers, build in cold regions, or choose technologies that blend into the natural background. The most advanced society may not be the brightest one. Closer to home, the search becomes physical. A probe crossing the solar system would not need to transmit continuously. It might be inactive, damaged, or designed to observe without drawing attention. An artifact could rest on an asteroid, orbit a distant moon, or travel through the outer solar system where human surveys remain incomplete. Airless surfaces can preserve objects for long periods, but space is not perfectly protective. Radiation alters materials, impacts accumulate, orbits change, dust covers surfaces. A machine left millions of years ago may no longer resemble a machine, even if it survived at all. Searching nearby objects for artifacts is scientifically possible, but difficult. The Moon, Mars, asteroids, and the outer solar system contain more terrain and volume than humanity has examined at high resolution. A strange shape in an image is not enough. Nature produces fractures, shadows, geometric crystals, and accidental alignments that can look designed when seen from far away. The same rule follows every technosignature search. An unusual observation is the beginning of an investigation. It is not the end. Researchers compare independent instruments. They repeat measurements. They test whether the signal moves with the sky or remains fixed to Earth. They examine known satellites, aircraft, stellar behavior, atmospheric chemistry, and detector effects. Most candidates disappear somewhere in that process. That is not disappointment. It is how a search becomes trustworthy. The great silence is often imagined as though humanity had called into every corner of the Milky Way and received no reply. In reality, we have begun to sample a narrow and complicated landscape of possible evidence. We have listened to some frequencies around some stars for limited periods. We have searched for certain kinds of laser pulse. We have examined parts of the infrared sky for unusual heat. We are beginning to consider atmospheres, artificial illumination, orbital structures, and artifacts within our own system. The search is wider than it once was, but it is still young. Perhaps there is nothing to find. Perhaps the signs are too faint, too brief, too distant or too unlike the technologies we know. For now, the galaxy has not failed to answer every question. We have only begun learning how many different questions can be asked. Somewhere between a lifeless planet and a civilization capable of leaving a mark among the stars, the path may narrow. This possibility is known as the Great Filter. The phrase does not describe a discovered force, a hidden wall, or a known event waiting at the same point in every civilization's history. It is a way of reasoning about a sequence. A suitable world must form. Its environment must remain stable enough for complex chemistry. Life must begin. That life must survive long enough to change. Simple cells may need to become more complex cells. Multicellular organisms may need to appear. Nervous systems, memory, learning, language, and cumulative culture may have to develop. A species must gain access to useful materials and energy. Knowledge must pass from one generation to the next without being repeatedly lost. Then technology must become detectable. After that, the civilization must remain present. It must survive natural hazards, its own inventions, and the social difficulties created by increasing power. It may need to build machines that can cross interplanetary space, then, perhaps, interstellar space. It must also choose to do so. Each step has occurred at least once because we are here. What we do not know is how often any of them occur elsewhere. The Great Filter asks whether one or more of these transitions is so unlikely that almost no world completes the full journey. Imagine a long corridor with many doors. The first door opens when a rocky planet forms in a suitable system. The next opens when stable chemistry becomes possible. Another leads to self-replicating life. Beyond that are complex cells, multicellular organisms, intelligence, technology, and long-term survival. A planet does not need to fail at every door. It needs to fail at only one. If each transition is moderately uncommon, the number of worlds reaching the far end can shrink quickly. A galaxy may begin with billions of planets and still produce almost no civilizations that remain visible for long. The filter may not be one dramatic barrier. It could be spread across several difficult transitions, each removing a fraction of the worlds that reached the stage before it. One candidate lies at the origin of life. On early Earth, non-living chemistry somehow became biology. Molecules began participating in systems capable of maintaining themselves, reproducing, and changing through evolution. Researchers have identified many pieces that may have contributed to this transition. Organic molecules can form naturally. Membrane-like structures can assemble under suitable conditions. Some molecules can store information or assist chemical reactions. But a complete explanation has not yet been demonstrated. No one knows how easily chemistry crosses into life. It may happen whenever water, energy, and the right materials remain together long enough. If so, living worlds could be common, or it may require a rare sequence of environments and molecular accidents. Earth may have offered countless chemical experiments before one produced a system able to persist it and evolve. The timing on our planet does not settle the question. Life seems to have appeared relatively early in Earth's history, after the surface became stable enough to support it. This could suggest that life begins readily, but observers can arise only on planets where life began early enough to leave time for complexity and intelligence. We should therefore expect to find ourselves on a world with an early beginning, even if such beginnings are rare. The next possible filter may lie within life itself. For much of Earth's history, living organisms were single-celled. They occupied oceans, sediments, rocks, and perhaps many other environments, but they did not build large bodies or nervous systems. The transition to complex cells took an immense amount of time. Modern complex cells contain specialized internal structures. Among the most important are mitochondria, the small energy-producing components found in nearly every cell of animals, plants, and fungi. Evidence indicates that mitochondria began as free-living bacteria. At some distant point, one cell entered another. Instead of being destroyed, it survived. The two organisms formed a partnership that became permanent. Over time, the internal bacterium lost much of its independence and became part of the larger cell. This event, or a related series of events, changed the possibility available to life. Complex cells could support larger genomes, more specialized structures, and new forms of cooperation. Eventually, some of them joined into multicellular organisms. If the origin of complex cells depends on a rare biological merger, then many inhabited planets may remain microbial for their entire histories. The world can be full of life and still produce no forests, animals, eyes, voices, or machines. Multicellularity is another uncertain step. Cells must cooperate while limiting competition among themselves. They must specialize, communicate, and regulate growth. Bodies need ways to transport nutrients, remove waste, repair damage, and reproduce reliably. Multicellular life has evolved more than once on Earth, which may suggest that the general transition is not unique. But complex animal life required much more than cells living together. It required long environmental stability, sufficient energy, ecological interaction, and evolutionary time. It also depended on earlier changes in oceans and atmosphere. For most of Earth's history, there was not enough oxygen to support large active animals. Photosynthetic organisms gradually altered the planet. Oxygen accumulated first in the oceans and later in the air. This transformation was not arranged for the benefit of future animals. It was the consequence of microbial metabolism operating over geological time. Only after the environment changed could new kinds of bodies become possible. Intelligence adds another narrowing. Many animals perceive their surroundings, solve problems, remember individuals, and communicate. Some use tools, some learn by watching others, some maintain complex social relationships. Yet none besides humans has created technology visible from another star. Human capability depended on a particular combination. Our ancestors had grasping hands, social learning, long childhoods, flexible language, access to fire, and environments where materials could be shaped. Knowledge could accumulate, rather than disappearing with each individual. A discovery made by one generation became the starting point for the next. This cumulative lead process may be more important than intelligence alone. A clever species living beneath a global ocean might never control fire. A species with short lives and little social learning might repeatedly rediscover the same tools without building upon them. A highly intelligent organism could lack the physical ability to manipulate its environment with precision. There is no reason to assume that evolution repeatedly produces astronomers. Natural selection favors traits that work within local environments. It has no awareness of distant stars and no preference for radio communication. Technology itself may create another filter. A species capable of altering its planet gains protection from some hazards. It can predict storms, treat disease, store food, monitor climate, and redirect small asteroids. The same capability can create new risks. Powerful tools may appear before institutions become skilled at managing them. Weapons can become more destructive. Industry can change atmospheres and ecosystems. Biological knowledge can be used carelessly or deliberately. Automated systems can spread mistakes quickly. Competition between groups may continue even after the consequences become planetary. A civilization does not need to vanish completely to become undetectable. Its population may decline. Infrastructure may fail. Knowledge may fragment. A society may remain alive while losing the ability to maintain observatories, transmitters, spacecraft, or industrial systems. It may recover later or it may not. The great filter becomes most uncomfortable when its location is considered. If the hardest barriers lie behind us, then humanity has already passed through the narrowest part of the corridor. Perhaps life almost never begins. Perhaps complex cells are rare. Perhaps technological intelligence depends on a combination of biological and environmental conditions that almost no planet provides. Under that interpretation, the silence of the galaxy would not mean that civilization inevitably ends. It would mean that very few worlds ever reach civilization at all. The night sky would be empty because the earliest steps are difficult. There is another possibility. Life may begin often. Complex organisms may be common. Intelligence may arise repeatedly. The hardest barrier may come later, after technology becomes powerful. In that case, silence. The science suggests that civilizations usually become quiet before spreading far. They may destroy themselves, lose technological capacity, choose isolation, or remain vulnerable to events they cannot prevent. Their detectable period may last only a few centuries, a brief interval beside the age of a planet. The galaxy could have produced many technological societies that never existed at the same time. One may have disappeared 1,000,000 years before humanity arose. Another may not appear for several million years after Earth is no longer habitable. Across cosmic time, the civilizations would pass like separate lights along an immense shore, each shining beyond the horizon of the others. This possibility is difficult to test because we know only one technological history. Humanity has been producing strong radio emissions for little more than a century. We have occupied space with machines for only a few decades. We do not know whether this stage is normally brief or whether it can continue for millions of years. We are trying to estimate the length of a road while standing near its beginning. The discovery of life elsewhere would change the question, but not answer it completely. If independent microbial life were found on Mars, beneath the ice of Europa, or in the ocean of Enceladus, it would suggest that biology can begin more than once. If simple life were detected on many exoplanets, the origin of life would appear less likely to be the main filter. Attention would then move toward later transitions. How often do complex cells appear? How often does multicellular life develop? How often does intelligence build technology? And how often does technology endure? A planet covered with microbes would not tell us that civilization is common. A world with forests would not prove that engineering is inevitable. Every discovery would remove one uncertainty while leaving others in place. The great filter remains a framework, not a verdict. It depends on assumptions about what civilizations do, what signs they leave, and how capable our searches are of finding them. If advanced societies are small, efficient, short-lived, or uninterested in expansion, the galaxy could remain difficult to read without any single severe barrier. Still, the framework gives the silence a deeper shape. It reminds us that a planet is not a promise, life is not a promise, intelligence is not a promise, and survival, even after knowledge has reached the stars, is not guaranteed by knowledge alone. Somewhere along the long path from chemistry to a lasting civilization, the universe may ask for a combination that very few worlds can provide. A different explanation places the difficulty much earlier, not at the rise of technology, but in the long preparation required for complex life. This is the central idea behind the rare Earth hypothesis. It does not claim that Earth must be the only living world. Microbial life could exist in many places. The narrower suggestion is that worlds able to support large complex organisms for billions of years may require a combination of conditions that does not occur very often. A planet must first form around a star capable of lasting long enough. Massive stars burn brilliantly, but their lives are brief. Some exhaust their central fuel in only a few million years. Planets may form around them, Yet biology would have little time to move from chemistry toward complex ecosystems before the star changed or died. Smaller stars endure much longer, but many have active youth. Flares and streams of charged particles can strike nearby planets with intense radiation because a dim star's habitable zone lies close to its surface. Any warm planet must remain within reach of that activity. The Sun occupies a useful middle ground. It is stable enough to provide billions of years of relatively consistent energy, though it has never been perfectly calm. Its brightness changes gradually, and the young Sun was fainter than it is today. Earth's climate survived those changes through a complicated relationship among atmosphere, oceans, rocks, living organisms, and the low evolution of the star itself. Distance from a star is only the beginning. A world within the habitable zone may receive enough energy for liquid water, but its atmosphere determines what that energy actually does. Venus and Earth are similar in size and formed in neighboring regions of the solar system, yet their surfaces followed radically different paths. Venus developed an atmosphere dominated by carbon dioxide. Its surface became hot enough to melt lead. Mars, farther from the Sun and much smaller than Earth, lost much of its early atmosphere and now holds liquid water only under limited conditions. If it remains present at all, Earth stayed between those extremes. Its oceans absorbed and moved heat. Clouds reflected some sunlight back to space. Greenhouse gases prevented the surface from freezing completely. Rocks and weather helped regulate atmospheric carbon over immense periods. The balance was never fixed. Earth has experienced severe ice ages, warm greenhouse climates, mass extinctions, changes in sea level, and shifts in atmospheric chemistry. Habitability did not mean permanent comfort. It meant that after disruption, conditions repeatedly remained within a range that life could survive. Geology may have helped. Earth's outer shell is divided into moving plates. In some regions, new crust forms. Elsewhere, older crust descends into the interior. This motion connects the surface to deeper layers and contributes to a carbon cycle operating across millions of years. Volcanoes release carbon dioxide. Rainwater reacts with exposed rock, gradually removing some carbon dioxide from the atmosphere. Rivers carry dissolved material toward the oceans. Part of it becomes locked into sediments and eventually returns to the interior as tectonic plates move. This process can act as a slow climate regulator. When the planet warms, weathering may increase and draw down more carbon dioxide. When the planet cools, weathering can slow while volcanic activity continues, adding gas to the atmosphere. The system is neither simple nor perfectly stable, but it may have helped Earth void, remaining permanently frozen or overheated. Scientists do not know whether plate tectonics is required for complex life. Another planet might recycle carbon through different processes. Its crust could move intermittently. Volcanism might occur without large plates. Oceans and atmosphere could exchange material in ways not found on Earth. With only one inhabited planet available for comparison, it is difficult to identify which features are necessary and which are merely part of our own history. Earth's moon is another possible factor. It is unusually large relative to the planet it orbits. Its gravity raises tides and influences Earth's rotation. It also helps limit the range through which the planet's axial tilt changes over long periods. The tilt of a planet affects its seasons. If that angle changes greatly, sunlight can be redistributed across the surface, altering ice, oceans, and climate. The moon may have reduced some of those variations, contributing to long-term environmental stability. But the importance of this effect remains uncertain. Computer models suggest that an Earth without its present moon might still remain habitable. Its climate could be less regular, but not necessarily hostile to all complex life. A large moon may be helpful without being a universal requirement. Jupiter has also been given a protective role in many descriptions of Earth's history. Its gravity can capture comets, deflect them, or eject them from the solar system. This has encouraged the image of a large outer planet standing guard over the inner worlds. The real effect is more complicated. Jupiter can remove some dangerous objects, but it can also disturb asteroids and comets in ways that send them toward the inner solar system. Whether it protects Earth or increases the number of impacts depends on the original population and orbit of those objects. There is no simple shield. The same gravity that clears one path can redirect another traveler inward. Impacts themselves have played conflicting roles. Large collisions can devastate ecosystems. One such event contributed to the extinction of non-avian dinosaurs around 66 million years ago. Yet earlier, impacts may also have delivered water to the young Earth, though the amount and importance of that delivery, the subject remains subjects of research. A planet may need enough impacts to mix and supply material, but not so many that complex ecosystems are repeatedly erased. Its size matters as well. A small world cools more quickly and may lose geological activity. Its weaker gravity makes it harder to retain a substantial atmosphere. A very massive, rocky planet could hold a dense envelope of gases, creating pressures and temperatures unlike those found on Earth. The amount of water may also need to fall within a useful range. Too little water can limit chemistry and climate regulation. Too much can cover the entire surface beneath a deep ocean. On such a world, high-pressure ice might form between the liquid ocean and the rocky interior, reducing the exchange of minerals needed by some forms of biology. Yet a global ocean is not automatically lifeless. It may support ecosystems unlike any on Earth. What remains uncertain is whether it would provide the environmental variety, energy gradients, and access to materials needed for complex technological organisms. Continents may have contributed to that variety here. Coastlines, shallow seas, rivers, wetlands, mountains, deserts, and changing climates created many ecological settings. Life adapted differently in each one. Isolation separated populations. Reconnection brought them into competition. Geological change repeatedly rearranged the stage on which evolution worked. Complex life also required oxygen. For a large portion of Earth's history, oxygen was scarce in the atmosphere and oceans. Photosynthetic microorganisms gradually released it as a byproduct. Much of that oxygen first reacted with iron and other materials before it could accumulate in the air. Only after long biological and geological changes did oxygen reach levels that could support large, active animals. The atmosphere we breathe is therefore not simply the background of life. It is partly a product of life. On another planet, biology might transform its environment in a different way. It may use other chemical pathways or rely on a solvent unlike water. Still, any complex ecosystem is likely to depend on a sustained flow of energy and a stable method of exchanging materials. The larger galactic neighborhood may matter too. Closer to the center of the Milky Way, stars are packed more densely. Supernovae may occur more often. Gravitational interactions can disturb planetary systems. Radiation from energetic events may reach planets more frequently. Farther from the center, the galaxy contains fewer heavy elements. Rocky planets require material created by earlier stars. Regions with less carbon, oxygen, silicon, iron, and similar elements may form fewer solid worlds, or worlds with different compositions. This led researchers to consider a galactic habitable zone, a broad region where planetary systems may possess both sufficient heavy elements and a comparatively stable environment. Its boundaries are uncertain. Stars move through the galaxy. Conditions change with time. A system born in one region may travel through another. Even near the galactic center, protected environments could exist. Farther out, rocky planets may still form. The concept is useful, but it should not become another rigid border around possibility. From where you are resting now, Earth can seem like a stable platform beneath an almost unchanging sky. But the stability around you was assembled gradually. The ground has moved through plate collisions and continental drift. The atmosphere has been rebuilt by organisms too small to see. The moon has drawn tides across changing coastlines. The solar system has traveled around the Milky Way many times, while nearby stars came and went. Every ordinary breath belongs to a planetary history billions of years long. The rare Earth hypothesis asks whether that history required an uncommon arrangement. Perhaps the galaxy contains many worlds with microbes beneath ice, in warm oceans, or inside porous rock. Perhaps biology begins often, but remains simple because its planet never develops enough oxygen, enough stability, or enough environmental variety for large organisms. A living Milky Way could still be a silent one. There is a danger, however, in treating every feature of Earth as indispensable, because this is the only inhabited planet we know. Every part of it can appear special. We have a large moon, so a large moon seems necessary. We have plate tectonics, so moving plates seem essential. We have continents and oceans in a particular balance, so that balance begins to look like a universal rule. This reasoning can turn biography into law. A different world may reach complexity through another path. It might orbit a cooler star and survive beneath a thick atmosphere. It might have no moon, yet maintain a stable tilt through the influence of other planets. It could support life beneath an ocean, where chemistry is powered by the interior rather than sunlight. The conditions that produced humans are not necessarily the only conditions that can produce observers. Still, the rare Earth idea offers a useful correction to simple optimism. A small rocky planet in a habitable zone is not already another Earth. It is the beginning of a much longer investigation. Its atmosphere must be measured. Its star must be understood. Its oceans, geology, climate, chemistry, and history must somehow be inferred from light gathered across an enormous distance. Complex life may depend not on one perfect condition, but on many imperfect systems remaining within workable limits for a very long time. That may be the uncommon thing, not the presence of water on one afternoon, not a comfortable temperature during one orbit, but continuity across billions of years while stars brighten, climates shift, continents move, impacts occur, and living organisms slowly change the world that carries them. The Milky Way may be old, but age alone does not tell us where we stand in the full history of life. The universe is about 13.8 billion years old. That number can make the present feel very late, as though nearly everything that could happen should already have happened somewhere. But the future may be far longer than the past. Many stars will continue shining long after the sun is gone. The smallest red dwarfs consume their fuel with remarkable patience, while a star like the sun remains on the main sequence for roughly 10 billion years. The least massive red dwarfs may shine for trillions. If planets around those stars can support biology, then most of the universe's opportunity for life may still lie ahead. The first stars could not have formed Earth-like worlds. Soon after the beginning of cosmic expansion, ordinary matter consisted mainly of hydrogen and helium, with small amounts of a few lighter elements. There was almost no carbon for complex organic chemistry, no oxygen for water, and little silicon or iron for rocky planets. Those ingredients had to be made inside stars. Fusion built heavier nuclei in stellar interiors. Massive stars later released enriched material through winds and explosions. New generations formed from gas, containing the remains of earlier ones. Only then could planetary systems gather enough solid matter to create rocky worlds, metal-rich interiors, atmospheres, and oceans. The universe required preparation, Galaxies had to assemble, stars had to live and die, their material had to spread through space and become part of new clouds. Those clouds then had to collapse into younger stars surrounded by disks where planets could grow. Life could not begin everywhere at once. The conditions for it emerged gradually. The solar system formed about 9 billion years after the universe began. By then, several generations of stars had enriched the Milky Way. Earth was not among the first possible rocky planets, but neither did it appear at the end of cosmic history. Other solid worlds may have formed billions of years earlier. Some could have offered stable environments long before the Sun existed. If life and intelligence usually develop on timescales similar to those on Earth, then certain planets may have had a considerable head start. That possibility strengthens the Great Silence. Yet the oldest planet is not automatically the first inhabited one. Early galaxies were more active. Stars formed rapidly. Massive stars exploded more often. Radiation environments could be harsher. Planetary systems may have experienced frequent disturbance. Heavy elements were present in smaller amounts and in different proportions. A world can be old without being stable. It may lose its atmosphere, freeze, overheat, or suffer repeated impacts. Its star may vary. Its orbit may change. Life may begin and disappear before complex organisms have time to emerge. Cosmic age is not a single uninterrupted opportunity. It is a collection of local histories. The future offers another kind of opportunity through red dwarf stars. Red dwarfs are smaller and cooler than the Sun. They are also the most common stars in the Milky Way. Because they use their fuel slowly, their lifetimes can exceed the current age of the universe by enormous factors. A planet around one could have far more time than Earth. Biology here required billions of years to move from its earliest forms to technological intelligence. Around a long-lived red dwarf, a stable environment might continue for hundreds of billions of years or longer. Time would not be the limiting resource, but red dwarfs create difficult conditions of their own. Because they are faint, a planet must orbit close to receive enough warmth for surface liquid water. At that distance, the star appears large in the sky, and gravitational tides can gradually synchronize the planet's rotation with its orbit. One hemisphere may remain turned toward the star, while the other faces away. This is called tidal locking. A tidally locked planet does not have to be sterile. A substantial atmosphere or deep ocean could move heat from the day side to the night side. Climate models show that air and water circulation may prevent the atmosphere from freezing out completely. A broad region between permanent day and permanent night might maintain moderate conditions. The larger concern may be stellar activity. Young red dwarfs can produce powerful flares. They release high-energy radiation and streams of charged particles. A nearby planet can receive repeated bursts that heat its upper atmosphere, alter its chemistry, and help carry gases into space. Some red dwarfs remain active for a long time. A planet may spend hundreds of millions of years close to a restless star before conditions become calmer. Its atmosphere might survive if it begins thick enough, if volcanic activity replenishes lost gases, or if magnetic and atmospheric processes provide protection. Water could also remain beneath the surface. Even a planet stripped of much of its air might preserve ice-covered oceans or underground environments, where biology could continue beyond the reach of stellar radiation. At present, astronomers do not know whether red dwarf systems are mostly hostile, occasionally habitable, or among the most productive homes for life. That uncertainty changes the meaning of cosmic timing. If red dwarf planets commonly support long-lived biospheres, then humanity may have appeared unusually early. The universe's most active biological era may begin after the Sun has become a remnant. In that case, the Milky Way could seem empty because few technological civilizations have arrived yet, we might be among the earlier observers rather than among the last. This idea does not remove the paradox. Many stars similar to the Sun are older than the Sun. Some rocky planets may have formed 1, 2, or several billion years before Earth. Even a small number of suitable, older worlds would provide enough time for life and technology to develop, provided the necessary steps are not too rare. The early arrival explanation therefore works best as one part of a larger picture. Perhaps humanity is early and life is uncommon. Perhaps simple biology begins often, but complex cells require rare transitions. Perhaps intelligence appears, yet technological societies remain visible only briefly. Several effects can operate together. The galaxy does not need one universal reason for its silence. Time also creates a problem of overlap. Imagine that technological civilizations arise occasionally, but remain detectable for only 10,000 years. On human scales, 10,000 years feels immense. Against the age of the Milky Way, it is almost nothing. Two civilizations could occupy the same region of space and still miss each other by millions of years. One might build radio telescopes, send probes, and disappear before the other planet develops complex animals. Its signals would continue traveling outward, but unless they happen to cross the later world during the brief period when someone was listening, no contact would occur. The galaxy could contain many histories without containing many neighbors at once. From a resting place on Earth, the night sky seems to present everything together. Stars of different ages appear on the same dark surface. Their light reaches your eyes during the same evening, even though it began its journey at different times. One star may be seen as it was 4 years ago. Another may be seen as it was 1,000 years ago. A distant region of the galaxy may appear as it was before human civilization began. The sky is not a single, present moment. It is an archive assembled by travel time. A civilization could be visible in one direction only as a past version of itself. Its planet may now be empty, transformed, or home to descendants who no longer use the technologies we could recognize. The farther away we look, the older the image becomes. This complicates every search. A signal arriving today from a star 500 light-years away was transmitted 5 centuries ago. Any reply from Earth would need another 500 years to reach its destination. A complete exchange would span 1,000 years. Institutions would change, languages would change. The civilization receiving the reply might not resemble the one that sent the first message. Contact across interstellar distance is also contact across time. This may explain why durable beacons would be more useful than conversation. A civilization could transmit repeating information for centuries, not expecting an immediate answer. It might send mathematics, maps, or scientific descriptions into space as a record that could outlive its original makers. Humanity has not found such a record, but our searches have covered limited distances, frequencies, and intervals. A beacon might repeat once each year, once each century, or only when a planet aligns with a particular star. We could pass through its beam between observations. The timing problem affects physical exploration as well. A probe may cross a planetary system during an era when no technological species is present. It may record oceans, clouds, and microbial life, then continue onward. Millions of years later, intelligence appears on that planet and finds no sign that anyone came before. The absence of a meeting does not prove the absence of travelers. It may reveal only that their journeys and our awareness did not coincide. Perhaps the universe has not remained silent for its entire history. Perhaps it speaks in brief intervals separated by ages too long for any one civilization to hear as a continuous conversation. Earth's own detectable period has only begun. Our planet has carried life for billions of years, yet, for almost all of that time, It produced no radio transmission, artificial night lighting, or spacecraft. A distant observer could have watched Earth through most of its history and found a living world without technological evidence. The present is a thin layer. So the Great Silence may partly be a problem of calendars. Stars form at different times. Planets stabilize at different times. Life advances at different rates. Civilizations may rise, change, and fade within narrow windows that rarely align. A galaxy can be full of possibility while leaving each observer alone in its own century. And beyond the lives of the stars we see tonight, much of cosmic time is still waiting to begin. One assumption has followed the Fermi paradox from the beginning. A successful civilization will grow. It will cross the space around its home star, build settlements elsewhere, and continue outward until its presence becomes difficult to miss. That expectation may describe some civilizations. It does not have to describe all of them. Growth is familiar to humanity because much of our history has been shaped by expanding populations, wider trade, new territory, greater energy use, and increasingly powerful machines. It is easy to extend that pattern into the future and imagine technological development as a steady climb toward larger structures and greater control. But no physical system can grow exponentially forever. A population that repeatedly doubles eventually requires more material than one planet can provide, an interstellar network that continues multiplying at the same rate eventually demands the resources of entire stellar systems. Even a civilization with advanced engineering must live within limits set by energy, matter, distance, and time. Long survival may therefore require something other than endless expansion. A mature society might stabilize its population. It might recycle nearly everything it uses, reduce waste, and maintain habitats for periods longer than any human institution has yet endured. Progress could come to mean reliability, knowledge, or depth of experience rather than the number of occupied worlds. Such a civilization might remain close to its home star. A single planetary system contains immense resources. Asteroids hold metal and rock. Comets contain water and other volatile material. Moons and small planets offer surfaces, caves, and stable orbits. Energy can be gathered from a star for billions of years. A society able to use those resources carefully may feel little pressure to travel farther. Interstellar settlement would also create separation. A colony 20 light years from its origin could not exchange a message and receive an answer in less than 40 years. Decisions would be made locally. Languages, values, and technologies would change. After several centuries, the settlement might no longer consider itself part of the civilization that launched it. Expansion across the galaxy would not necessarily create unity. It could create thousands of independent histories. Some settlements might continue traveling. Others might stop. A few could disappear. Machines might keep operating after the cultures that built them were gone. Descendants might alter themselves until the idea of one original civilization no longer carried much meaning. The Milky Way could contain scattered regions of activity without ever becoming a single connected society. Even widespread settlement might remain uneven. Stars are always moving through the galaxy. Distances between neighbors change. A system that is difficult to reach during one era may pass closer to another star millions of years later. Travel could occur in bursts, following temporary routes created by stellar motion. Some regions might be visited many times. Others could remain outside the network through distance, timing, lack of useful resources, or chance. Earth might occupy one of those gaps. This possibility does not require every civilization to reject travel. It only requires expansion to be irregular. A scientific group may send probes while the wider society stays home. A small community may leave for reasons that no longer matter to its descendants. An automated machine may continue moving after its instructions have become older than the civilization that created them. The galaxy could be neither empty nor fully settled. It could be patchy, and patchiness is difficult to recognize from one small planetary system. There are other ways for an advanced society to become less visible. Greater efficiency can reduce waste heat. Communication may move into narrow beams that rarely point toward Earth. Industry could shift away from planetary surfaces or into cold regions where energy is used carefully. A civilization might become more active inside computation while becoming less active across physical space. This possibility is speculative. Humanity does not know whether minds can exist in artificial forms, whether consciousness can be transferred, or whether machine societies represent a likely future for any species. But the idea shows why advanced does not always mean bright. A civilization may become harder to detect as its technology improves. Silence could also be a choice. The most famous version of this idea is called the dark forest. It imagines the galaxy as a place where civilizations avoid revealing themselves because they cannot know the intentions of distant neighbors. The name comes from science fiction, and the concept should not be mistaken for an established scientific theory. No evidence shows that hidden civilizations are watching one another or that contact between them is dangerous. The dark forest is a thought experiment about uncertainty. Suppose a civilization detects a signal from a world 100 light-years away. The signal describes a society as it existed 100 years in the past. Any reply will need another century to arrive. By then, the distant civilization may have changed completely. Its governments may be different. Its technology may be more powerful. The people who sent the original message may no longer exist. Trust would have to cross not only distance, but generations. A message can describe friendly intentions. It cannot guarantee what the sender will become. The receiving civilization faces the same problem. It may want cooperation, yet it cannot know whether revealing its location creates a risk that cannot be reversed. Once a signal travels outward, it cannot be recalled. Fear might therefore encourage restraint. A society could reduce radio leakage, avoid powerful beacons, and communicate only through tightly directed systems. An inhabited galaxy might appear empty because its civilizations have learned not to announce themselves. This reasoning contains many assumptions. It assumes that civilizations fear one another. It assumes they can hide effectively. It assumes that potential danger outweighs curiosity, cooperation, and the value of shared knowledge. It also assumes that remaining undetected is possible. After a society has altered its planet or used large amounts of energy, none of those assumptions is confirmed. The Great Silence is not evidence of cosmic predators. It can be explained without hostility through rare life, short technological lifetimes, difficult travel, narrow communication, or searches that remain incomplete. Still, the dark forest raises a real question for humanity. Should we deliberately send powerful messages toward other stars? Some researchers and organizations have transmitted intentional signals. These efforts are often called messaging extraterrestrial intelligence. Supporters argue that Earth's atmosphere has revealed signs of life for a very long time, and that advanced observers may already know this planet is inhabited. They also note that meaningful contact could expand scientific understanding beyond anything available from one world. Critics focus less on the probability of danger and more on authority. A transmission from Earth speaks from one planet, but no person or institution has been chosen to represent every human being. The decision could affect generations who had no part in making it. For now, the debate remains theoretical. No confirmed recipient is known. No reply has arrived. Yet every message sent into interstellar space becomes a record of our time. It carries the language, science, and assumptions of the people who created it. If someone receives it centuries from now, they will not meet humanity as it exists then. They will encounter a preserved fragment of an earlier generation. Our radio waves are already doing this unintentionally. Some emissions have traveled more than 100 light years from Earth. Within that expanding region, a sufficiently sensitive observer might detect traces of 20th century technology, though ordinary leakage becomes faint quickly and would be difficult to recognize. Across such distances, the farther those signals move, the older the humanity inside them becomes. Another speculative explanation is the zoo hypothesis. It proposes that advanced civilizations may know Earth is inhabited, but choose not to interfere. They might observe from a distance, waiting until humanity reaches some technological or social threshold before making contact. The comparison is usually made with a protected reserve. Observation is allowed, interference is limited. This idea can sound less threatening than the dark forest, but it faces a serious scientific problem. Almost any absence of evidence can be explained by saying the observers are good at hiding. A proposal that can explain every possible observation is difficult to test. There is no confirmed evidence that Earth is being monitored, protected, isolated, or examined as part of an experiment. The value of these ideas lies less in their likelihood than in what they reveal about our assumptions. The Fermi paradox often imagines civilizations that behave as humans expect ambitious civilizations to behave. They expand, transmit, build large structures, and remain interested in distant worlds. But intelligence may not produce one universal culture. Some societies may explore, some may remain local, some may communicate widely. Others may find no reason to speak beyond their own system. The galaxy could contain many answers at once. Our difficulty is that almost all of them look the same from Earth. They look like no confirmed signal, no visible construction, no visitor, no reply. The silence may represent emptiness, or it may be the shared outward appearance of civilizations whose choices, technologies, and histories have little in common. To distinguish among those possibilities, speculation is not enough. The final question is not only why the galaxy has not answered, it is how carefully humanity has learned to listen.